gradient and the directional derivative. So far we learned that we learned about the rate of change of the function in the direction of x-axis and in the direction of y-axis, which we denoted them by f of x and f of y. So what's the meaning of that? It means that suppose you are walking on a mountain and you're interested in knowing what is the rate of change of the wind, the rate of change of the wind, how wind is moving, the rate of the change of the wind in the horizontal direction, and also in the vertical direction. Rate of change of the wind in the direction of the vertical direction. Okay. Now I expect you to ask, what if I want to know what is the rate of change of the wind in any other directions? How fast the wind is moving in any other direction? That's a legit question. Why not? Question. How do we find the rate of change of the wind in any other direction, or in the direction of a vector v equals to a and b? This is a vector. So I'm saying that, hey, suppose now I have this direction. This is my direction, v, and I'm interested in finding the rate of the change of the wind in this direction. How do I calculate that? Okay, there you go. To find this, we have a nice formula. We present the directional derivative or the rate of the change of the function in the direction of a vector. So please listen carefully. Let z be equals to f of x and y be a function. Let u equals to a comma b be a unit vector. Guys, this piece of information is important. If we are not using a unit vector, we have to convert the vector that we have to a unit vector. So suppose we have a function and u is a unit vector. What's the meaning of that? It means that the magnitude of u is equal to 1. The directional derivative is defined this way. The directional derivative of your function. F in the direction of your vector u is equal to. We need the partial derivative of the function. Partial derivative of f with respect to x times the first coordinate of your vector plus the partial derivative of f with respect to y times the second coordinate of the vector. So this is the directional derivative of your function in the direction of u. The directional derivative of function f of x and y in the direction of vector u. Very well. Let's go over one example. I'm going to leave the formula down here. So this example says, find the directional derivative of what is the function f of x and y equals to, well, we have x cubed minus 3xy plus 4y squared in the direction of let's find, okay, in the direction of vector v square root of 3 and 1. Okay, let's see what we have here. If z is a function and u is a unit vector, we have the function z. Now we have to think about this vector. Do we have a unit vector? So question. Check if v is a unit vector or not. Very well. So this guy is not a unit vector. No. Why is that? The magnitude of this vector is equal to square root of, we take the first component, raise it to the second, so square root of 3 to the second, plus we take the second component, raise it to the second power, which is square root of 4, which is 2. It is not 1. It's not a unit vector. So what should I do then? Using the directional derivative says, hey, you need to have a unit vector. Unit vector, okay, how do I convert this into a unit vector? Oh, I reminded myself that in math, once in elementary calculus, I learned that, hey, if I divide the vector by its magnitude, then I can create a unit vector. U is equal to V divided by the magnitude of V. So I get square root of 3 divided by 2, a half, which is a unit vector. Now I'm happy with it. I'm going to use this vector, follow the formula, then I'm done. So the formula says I need to have the partial derivative of f with respect to x, partial derivative of f with respect to y. So the directional derivative of function f of x and y is going to be f of x a plus partial derivative of f with respect to y times b. Okay, the rest is not that hard. Finding the partial derivative with respect to x, this guy is equal to 3x squared minus 3y times a. A is square root of 3 divided by 2. A is square root of 3 divided by 2. Okay, let's just put that guy here. Plus, and here, partial derivative of f with respect to y is going to be negative 3x plus 8y. So this is partial derivative with respect to y. And b, what is b? b is a half. So this is the directional derivative or the derivative of the function in the direction of u. And if they have different points, you can easily calculate this rate of change in the direction of vector, unit vector u. So if we are given different points, we can find the rate of change at that point. There you go. So sometimes instead of having the vector itself, they might give you the angle that the vector makes with positive part of x-axis. So in that case, we can write down the directional derivative using the angle that we have. So note that sometimes we are given the information about the angle, like theta, that the vector, unit vector, makes with positive part of x-axis. Then the directional derivative of function f in the direction of vector u is equal to partial derivative of f with respect to x, or the rate of change of function with respect to x times cosine of theta plus the rate of change of the function in the direction of y-axis times sine theta. Another note, we can take the partial derivatives of the function and define, let's get back to elementary calculus and define a vector function which is denoted by delta upside down f or nabla f that we call the gradient of the function. So you have the gradient of function f, which is denoted by a vector function. So we're going to use the vector symbol, the vector notation. The very first component is partial derivative of f with respect to x, comma, the second component, partial derivative of f with respect to y. So we have a vector function that we call the gradient of f. There we go. So remember that we defined the directional derivative this way. We said that, hey, the directional derivative of function z equals to f of x and y, and in the direction of the unit vector. Again, guys, unit vector. Like u equals to a and b is d of f of x and y in the direction of u, f of x, a, plus f of y, b. Well, what do we see? We see partial derivative with respect to x, partial derivative with respect to y. Remember what we learned in elementary calculus. Let me write down this recall for you here. Recall the dot product between two vectors. If you have vector AE dot product CD, the outcome is AC plus ED. Remembering from elementary calculus, we can write the directional derivative as the gradient function dot product with the unit vector a and b, or the directional derivative of f in the directional vector u is the gradient that we just defined dot. Another representation in compact, nice form of using the gradient function, gradient vector function, and your directional derivative. There we go. One important observation is that the directional derivative or the rate of change of the function in the direction of u is going to be maximized, and it's equal to the magnitude of your gradient function, and when u is in the direction of your gradient function. So note that directional derivative of f has maximum value, which is the magnitude of the gradient of f, which is equal to square root of partial derivative of f with respect to x squared plus partial derivative of f with respect to y squared, and it is in the direction of, and u is in the direction of the gradient function. So give us an example. What are you talking about? Well, okay, let's see. So in this example, the question says, let f of x and y be equals to x e to the y. X e to the y, okay. Question says, find the rate of change. Find the rate of change. How fast it is increasing, decreasing, the rate of change of function at the point, like P. The point is 2 and 0 in the direction of what? Direction of P to point Q, which is 1/2 and 2. Then B, it says, what is the maximum rate of change? So we're going to answer 2 questions. First, for this function, we want to know what is the rate of change at this point in the direction of this vector. So first, we need to identify the vector, make sure this is a unit vector. Let us find the vector first. Okay, so from P to Q, we're going to have the vector 1/2 minus 2, comma 2 minus 3. So the first component of the vector is negative 3/2, and the second component is 2. This is my vector. Is this a unit vector? Okay. We need to find the magnitude. The magnitude is 9/4 plus 4, which is equal to square root of 25/4, or 5/2. It's not equal to 1. It's not a unit vector. So we need to convert that into a unit vector. U is equal to PQ divided by the magnitude of PQ. Okay, so here I have negative 3/2 divided by 5/2 and 2 divided by 5/2, which is equal to, write this down here, negative 3/5 and 4/5. This is my unit vector. Now the rest is easy, finding the directional derivative in the direction of this vector. The directional derivative of function f in the direction of u is equal to. And the point is given as 2 and 0. So let us write 2 and 0 here. Then the partial derivative of f with respect to x, which is e to the y is 0, times the first component, negative 3/5, plus partial derivative of f with respect to y, which is x times e to y, x is 2, 2 times e to my y is equal to 0, times the second component, which is 4 over 5. So this guy is equal to, this is just 1, negative 3 over 5 plus 8 over 5, which is 5 over 5, or 1. This number is the rate of change of my function in the direction of this vector. This is the rate of change of the function in the direction of u. Well, is this the maximum rate of change? We're about to find it out. What is the maximum rate of change? We know the maximum rate of change is the gradient of f magnitude. So we get the square root of, well, remember that the gradient of f, as we calculated that, is equal to f of x, comma f of y. My f of x is just e to the y. My f of y is x e to the y. At the given point, this is equal to e to 0 and 2 times e to 0, or 1 and 2. So I get 1 squared plus 2 squared, which is equal to square root of 1 plus 4, or square root of 5, which is larger than 1. This is my maximum rate of change. Maximum rate of change. If my vector u is in the direction of 1 and 2, they are moving along each other. Moving along each other. It happens when the gradient vector and the unit vector are in the same direction. Remember that we say two vectors are in the same direction. Let me write it down here. We call two vectors like u equals to a and v equals to c and d are in the same direction or parallel to each other. If when you divide the first coordinates and second coordinates is equal to the same number. So now